you've pulled on the spring wants to stretch back up. So if you let go, you'll see this oscillates. We're going to look at simple harmonic motion. So this is a mass on a spring. We have a couple masses here, putting some weight here on the spring that's pulling down. So let's see, starting off, it's not moving. At this point, there's some force of gravity pulling this down. Then the spring itself is also pulling up. The two forces are in balance, so this is not moving here. It's staying still. So if you do pull on this, so now you've pulled on the spring wants to stretch back up. So if you let go, you'll see this oscillates. And it oscillates as a simple harmonic oscillator. So what that means is that as this is being here, once it's fully stretched, then there is a force pulling it to restore back to where it was, but then overshoots. It goes past its kind of equilibrium point. So if you look at this point here where it doesn't move, you'll notice that once it's going back up, it overshoots that and ends up here. Now the force is downward. It switches back and forth. So down here, it wants to go up. Once it's up here, it wants to go down. So that force, the fact that the net force switches, means that this will oscillate back and forth like that. So let's see that in motion. So if you see that, it goes up and down in a simple harmonic fashion. We can see what happens if you reduce the mass here. So if you have less mass, what happens to it? The equilibrium point is further up, so the spring is less stretched because it's less mass on it. So now if you do the same thing, if you let go, you'll see now it moves a lot more. It has a greater motion here. So you can see the difference, and you can try to figure out how to calculate the spring constant as a result of knowing how they move as a result of having different masses on it.